Hello everyone, welcome to part 20 of my video series on sampling. Now, the video series is not really about sampling, it's about probability distribution, but I thought that it is a very important topic to understand how to sample from a probability distribution because this is something you use a lot in real life and I didn't really find very good resources in the internet on this, so I thought of clearing this concept. So let's dive in the concept of sampling. So first of all, what does sampling mean in the context of a probability distribution? The definition is somewhat like this. You randomly pick an instance of the random variable and you do that in accordance with the distribution PMF or probability mass function in the discrete case or the PDF probability density function in the continuous case. So what do I mean by that? So let's look at this particular graph right here. It's a plot of standard normal PDF and you can see that the mean is 0 and standard deviation is 1. Now, if we want to sample a random variable from this distribution, we are basically randomly choosing a value of x. That is what sampling means. But when we are randomly choosing a value of random variable x, we have to do it according to the PDF given right here. So what does that mean? You can see that in this red area right here, the probability density is quite high. That means it is highly likely that if you randomly sample a point from this x-axis from the random variables, it should come from this narrow region because the density is so high here. On the contrary, these two areas, their PDF, their density is actually very low. So it is highly unlikely that the randomly sampled point will actually come from any of these areas. To be more concrete, if you sample maybe 100 points, 100 instances of random variable x, then most of those instances will come from here. Some will come from here, and very few will come from the tail. So that is what random sampling actually does. Now the question is, how do we do the random sampling? Now, the obvious answer is you can use a library. You can tell the library how many points you want. You can also tell the library what is your PDF or probability density function, and the library will do the work for you. But if you really want to understand how the library is doing this, bear with me. So first of all, let's talk about the case of discrete probability distribution. So how are we going to sample one random variable instance from a discrete probability distribution? Because if we can sample one random variable instance, we can also sample 1000 instances following the same procedure. Okay, so this is a discrete probability distribution, which is the Poisson distribution. So let's see what it means. So k equal to 10, k is the random variable. At k equal to 10, you can see that the value in the y-axis is something around 0.13. That means there is a 13% chance of us seeing 10 events in a single unit time, right? That is what it means. Now, if you want to know more about Poisson distribution, I have a separate video on this. So make sure to check that out. I will put the link in the description. In that particular video, I also derived the CDF, the cumulative density function or distribution function of Poisson. And that is actually very simple. It is nothing but probability of x less than equal to k, where k is the random variable. So what does that mean? Just to clarify. So at this point 10, you can see that we have a value of around 0.6. That means there is 60% chance, there is 60% probability that in a single unit time, we are going to see 10 or less number of events. That means in a single unit time, you can see 0 event, 1 event, 2 event, up until 10 events. So what is the summation of all of that, right? That is basically this value. That is called CDF. Now, the first thing we have to do is we have to construct the CDF. That is the first thing we have to do. Then we have to generate a random number from a range of 0 to 1 because the y-axis has a range of 0 to 1 with uniform probability, basically. And you can guess that maybe that number is 0.55. I mean, it can be anything, but I'm just putting a random number here, 0.55, and it sits right here. What we are going to do now is we are going to simply draw this line, right? Now, we have to go through these points and their CDF values, and we have to find the point, find the smallest point, smallest value of k, where the CDF value is just above this particular value. For example, you can see that at k equal to 10, for the first time we are getting a CDF value which is higher than 0.55. So the sampled instance here will be 10. Another example you can actually see here is, suppose we have again generated another random number in a range of 0 to 1, and that number is maybe 0.05. And in that case, you can see when we have k equal to 5, that is the first time we are actually surpassing, right? We are surpassing the value of 0.05 as the CDF right here. You can see the CDF is above. That means the sampled instance will be 5 right here. So that is very simple. That is how discrete probability distribution is actually done. But what about the continuous case for the same thing we want to achieve? So for the continuous case, we can look at standard normal PDF, and obviously we can get this particular CDF plot right here, where we have f of x less than or equal to x, right? Same thing. That means at a value of 0, we have around 50% probability. That means we have a 50% probability of seeing random variables 0 or even less, right? So the variable value can be -4, -3.6, 3.88, or anything. So anything less than 0, what is the cumulative probability of those? That is 50% right here. Okay, now let's again start by generating a random number, and that random number is maybe 0.45 right here. This time the issue is we cannot really get away so easily as the discrete case. The obvious thing is we have to get an x, a random variable x, such that the CDF for that x is very close to 0.45. But it is not so straightforward, because you can see that just in between -1 and 0, there can be infinite possible x values. There can be -0.99, -0.995, -0.001, and so on and so forth. So we cannot just say, let's get the smallest possible x, where probability of x less than or equal to x is bigger than 0.45. We cannot say that. Okay, so what are we going to do? There is a method called bisection method in numerical methods, which we can use to derive the instance, the random instance. So I'm going to show you that right now with an example. So this was the value we are interested in. These are our two extreme cases. We can first take the average and get right here. What we are going to try and see is, does the CDF value of these 2 points cover this particular red dot? Yes, they do. But if you take the CDF value of these 2 points, they don't really cover the red point. So we are going to take these 2 points in the next iteration. You can see that we have taken these 2 points and we have again taken the average, right? Okay, fine. If this is the average, then what? Again, we ask the same question. Does the CDF of these 2 points cover the red point? No, they don't. But these 2 points do. So these are our 2 new points. These are the next iteration. So we have this next iteration points. Again, take the average, ask the same question, which pair actually covers this point? So these 2. Again, we take the average, ask the same question, take the average, ask the same question, take the average, ask the same question. And now, when we have the average, we see that the average is extremely close to the generated random number, which was 0.45. And so we can take this blue point right here as our sampled instance. It's a bit lengthier than the discrete case, but it is what it is. This is what we can do to generate random sample instances of random variable of continuous distribution. Now, this procedure will work for any continuous distribution. The previous procedure that I showed you for discrete distribution will work for any discrete distribution. So this is how sampling is done in probability distributions. If you like the video, feel free to subscribe and share. And you can direct to our channel to the link in the description. Thank you very much.